All right, class, today we're going to be talking about rates of change and behaviors of graphs. So something to know is that a rate of change describes how an output quantity changes relative to the change in the input quantity. The units of rate of change are output units over input units, but you probably could remember it as delta y over delta x. Does this look familiar? I hope this is reminding you of the slope. So the average rate of change between two input values is the total change of the function values, the output, the delta y over delta x. So it's divided by the change in the inputs. So in this particular section, we're going to start seeing something like this. And I hope that this looks familiar to that y1 minus, or y2 minus y1. So now notice how we're just changing it to include that function notation. So for each of the following tables, right, of function values, find the average rate of change over the given interval. So we're using this equation here. So let's go ahead and check this out. So I'm going to start off with this one. So this is telling me, this is an interval, so keep that in mind. So this is telling me from 0 to 6. So I'm going to look at 0 here, and I'm going to look at 6 here. So I'm looking at my function values first. So I'm going to start off with, these are my function values. So let's go ahead and do 11 minus negative 2 all over, and then I have 6 minus 0. 11 minus 2, that gives me a positive 13, and then this is going to be over 6. So then this is my rate of change, also known as my slope. So we've been calling it a slope for a while. All right, so now let me erase these marks because now I'm looking at negative 1 and 20. So here's my negative 1, here's my 20. So what are my f of x values? Well, my f of x values are 4 and 16. So remember f of x, because it's the change in y over the change in x. So I'm going to have 16 minus 4 all over 20 minus negative 1. 16 minus 4, that's going to give me 12 over 20 minus 1 is going to give me 21. All right, next one, 4 and 6. So again, let's erase this. I'm looking at 4 and I'm looking at 6. The output values are 11 minus 7, and I got the 11 from here and the 7 from here, all over 6 minus 4. 11 minus 7, it's going to be 4 over 2, which is equal to 2. So that rate of change is 2. Okay. Let's take a look at B here. Again, kind of same notation, right? So here's 3/4. Yeah, let's change colors here. So here we have 3/4. So 3 and 4. I'm going to look at my y values of negative 1 and 2. So I'm going to start off with negative 1 minus 2 all over 4 minus 3. Negative 1 minus 2 is going to give me a negative 3. 4 minus 3 is going to give me 1. So then that rate of change is just negative 3. All right, let's take a look at 0 and 8. So here's my 0, here's my 8. So it's going to be 14 minus 6 all over 8 minus 0. 14 minus 6 is going to give me 8 over 8, which is 1. All right, our last one here is 5 and 3, looking at 2 and 2. So I have 2 minus 2 all over 5 minus 3, so I get a 0 over 2, which is equal to 0. So that's going to have a 0 rate of change, and it makes sense, right, because it's not changing at all in that y value. All right, let's take a look at looking at it from a graphical perspective. So for each of the following graphs, find the average rate of change over the given intervals. Remember, these are intervals. So here we have negative 3 and 2. So I'm going to be starting off, so when I look at delta y over delta x, I need to figure out what those y values are. So at negative 3, I'm going to come over here and I have 1, 2, 3. So I see that one of my points is going to be negative 3, comma 0. So my y value is 0 and my x value is negative 3. And for 2, I'm going to have, this is 1, this is 2, so I have this point here, and so this looks like it's 2, comma 5. And so I'm going to have 2, comma 5. So now this is going to look like 5 minus 0 over 2 minus negative 3. So this is 5 over 2 minus 3. That's also going to give me a 5. So this is going to be a rate of change of 1. Let's look at negative 2. So negative 2 is this point right here. And so this looks like it's going to be negative 2 comma 1, 2, 3. And I'm also going to look at 1. So here I'm at 1, and this looks like the point 1 comma 0. So let's look at, again, we're going to do delta y over delta x as our rate of change. Our y value is going to be 0 minus 3. Oh, that should be negative 3. Minus negative 3 all over 1 minus negative 2. So this is going to be 3 over 1 minus negative 2. That's also 3. So the rate of change is also 1. Okay. All right. Negative 2 and 2. So negative 2, I already have that point here. 2, 1, 2. I have this point already here. So let's take a look at that. So I'm going to have delta y again over delta x. So the changes in my y is going to be 5 minus negative 3 all over 2 minus negative 2. All right, so 5 minus 3, that's going to give me an 8 over 2 minus negative 2, which is going to give me a 4. So that rate of change is 2. And lastly, we have 0, 3. And actually, instead of 0, 3, we're going to go ahead and change this, and we're going to make this 0, negative 2, because I think that would be a little bit more interesting. So let's take a look at that. So at 0, from the interval from 0 to negative 2, if I look at this 0, it's going to give me this point 0, negative 3. And at negative 2, I'm going to get this point negative 2, negative 3. So when I look at this rate of change, that delta y over delta x, I take a look at this, I'm going to have negative 3 minus negative 3 all over negative 2 minus 0. All right. So then when I look at this from this particular interval, notice I'm going to have 0 over negative 2, which is just 0. And I do want to correct, because I did just change this last minute. So in reality, that correct interval should have been written as negative 2, 0, because we're going from the negative side to that positive side. But the reason why I wanted to change it to this one is that I think it's a little bit more clear just looking at the graph why that rate of change is in fact 0, because notice what happens here. I'm at this point, and as time goes by, I haven't changed. I'm back at this point. So even though that function changed, the rate of change between that particular interval from negative 2 to 0 did not change, because I'm back at that same value. So I thought that'd be a little bit more interesting than the previous interval I had there. Let's take a look at some of these now that we're going to calculate the rate of change given functions at specific intervals. So same thing, first we need to be able to figure out, well, remember these are at both x values because this is an interval. I'm going from negative 3 to 3. So I first need to figure out, okay, well, what is f of negative 3? So I'm going to plug that into the calculator. So I get 3 times 3 squared minus 2 times 3 plus 5. So take a moment to plug that into your calculator, as I'm doing right now. So I got 26, and now we're going to do this again with f of 3. So now we're going to have 3 times 3 squared. Oops, you know what? I plugged in positive 3 in that answer and not negative 3. So that means that this will actually equal 26. Let's go back and recalculate this one real quick, because I should have had a negative here. So that would have given me a 38. All right, so now let's calculate that rate of change. So now I have my two y values. So again, we're going to look at delta y over delta x. So my rate of change here is going to be 26 minus 38 all over 3 minus negative 3. So 26 minus 38, that gives me a negative 12. All over a negative, and a negative is a plus, so this is 9. So I end up with 12 divided by 9, which will simplify down to negative 4. So it'll be negative 4 over 3. All right, let's try the next rate of change. So I'm going to go ahead and erase this. So now we need to find out the value of 0 and 2. So if I plug in 0 here, we're going to get positive 5, and then I need to figure out the value of 2. So I get 13 here. Whoops, I keep clicking on that. Sorry, class. So then this gives me 13. So I come over here, and again, I'm going to do delta y over delta x. And then I should have 13 minus 5 all over 2 minus 0. So 13 minus 5, that's going to give us 8 over 2, which is 4. All right, our last one here. We already know what 0 is. 0 is going to be 5. So 0 is going to map to 5. But negative 1, we need to plug in. Let's figure out what negative 1 is. So I got 19 here. So then our delta y over delta x is going to be 5 minus 19 all over 0 minus negative 1. So the 5 minus 19 is going to give us a negative 14 all over positive 1, which is just a negative 14. So these are our rate of changes using functions, to find those values. All right, let's talk about looking at graph behavior. We talked a little bit about this on Tuesday, so we're going to focus a little bit more on this now. So, oops, why does this keep happening? Sorry about that. All right, so when we're looking at functions, particularly when we're looking at them when they're increasing and decreasing, I kind of wanted to mention one thing. So if I drew a graph, for instance, right here. So here's my graph. Change colors here. So let's say I had something that looked like this. Well, then from here to here, this would be called increasing, and we kind of talked a little bit about this on Tuesday. From here to here, this would also be called increasing. So basically, when we're talking about an increasing function, we're basically saying that our function f of, for instance, b is greater than our f of a, where b is greater than a. And so these b's and this a come from the fact that if I'm looking at a specific interval. So let's say that this is the interval I'm looking at, this is a, this is b. So as b, we can tell b is greater than a, right? So as b is greater than a, how is the function of f of b behaving in comparison to a? If the function is also greater, then that means that we have an increasing function. So basically, when we were talking about end behavior, as x goes towards, like, for instance, infinity, the function of f of x is also going towards that infinity. It's growing upward. Think of your lines, right? That's what it means to be increasing. Now, if I looked at that same interval, right, but instead of the function growing, the function starts decreasing, that's kind of what we see here in this next interval, right? Because from, for instance, this interval to this interval, you know, let's call this A and this B, as x grows towards B, the function itself is starting to go down. It is beginning to decrease. So that's what we call decreasing, right? And that is when B is greater than A for our x values, right? As we are getting larger, right, our actual function is decreasing. It's coming down. So the values of those functions are lower on the right side than they are on the left side. So let's take a look at the function here that we have in this particular example. This is a piecewise function because notice how it's broken up into different pieces. So we want to be able to acknowledge kind of where it's increasing and where it's decreasing. So increasing, notice if I took this interval here and here, right, as x is increasing, right, so as x is going towards the positive, right, we notice that the function itself is also growing. So that means that f of x is also increasing here, right? So it's growing. So this is an example of that f of b is greater than f of a. So that means that in this particular interval, we would call this the interval from negative infinity, because we can assume that the graph is going further down, all the way to the point -1 is increasing. Okay, is that the only point of increasing? No, because notice what is happening from this interval to this interval. Notice how the function is also increasing here. So because it's also increasing here, that is another interval of increase. So it's going from 0 to 2. This is another space where it is increasing. So because I have two different intervals where it's increasing, you probably already guessed that we are going to use the union sign to demonstrate the increasing intervals. So it'll look something like this. Okay. All right, let's take a look at a decreasing. So decreasing, just like before, it's when our function is going to kind of look like it's going down. So in our, oh my goodness, why does it do this? In our function here, I can look that from here to here, notice how the graph is going downward. So that would be where it's decreasing. So it's decreasing from -1 all the way to 0. That is our decreasing interval. Now a constant interval, that's where there is no change whatsoever. And so we can see here that from 2 to 6, or to infinity, positive infinity, it looks like it's going to remain constant. All right, let's talk about relative maximum and relative minimum. So in order to talk about that, we need to talk a little bit about what a local maximum is and what a local minimum is. So a value, so let's take this, let's kind of write down some vocabs real quick. So for a local maximum, so this is going to be a value of the input. So when the function changes from increasing to decreasing. Now, a local minimum is going to be a value of input. So the same thing. So value of the input when the function changes from decreasing to increasing. So let's take a look at what that really means. So in this particular case, we are going from an increasing function, so something that looks like this, to a decreasing function. Okay, and it could look something like this. It could look a lot of different ways, but notice how we are going from increasing, we're going up, we pause and we come back down, and that's decreasing. So this is what we will call a local maximum. Local and relative mean the same thing. So sometimes we'll see the word relative. Okay, so again, that's just a maximum that our function kind of reaches when it changes from increasing to decreasing. We use the word maxima or minima if there is more than one. So if it's plural, we use maxima or minima. If it is singular, we'll say maximum and local minimum. Okay, so that's just plurality, and like I said, relative and local are interchangeable. So if you're reading your textbook, you'll see the word local, but oftentimes relative is a little bit more heard. Now, there is a difference also so this is local or relative, and it's based off of being within a closed interval. So a function can have a local or relative maximum or minimum in a specific interval, but then they can also have what we call an absolute maximum and an absolute minimum. So let's take a look at an absolute max. So an absolute max, right? So the big difference between locating the highest and lowest points on a graph in a region around an open interval, so that's locally, so that's what we were just talking about here, and locating the highest and lowest points on the graph for the entire domain. So when we're talking about absolute max and min, we are looking at the entire domain. So the y-coordinates, the output at the highest and lowest points, are called the absolute maximum and the absolute minimum. But the biggest difference is that here we're looking at the entire domain versus looking at it relatively to an open interval. Okay, so when we're looking at this particular graph, here, let me erase all of my writing here. Looking at this particular graph, we can see that there might be locally to this interval, we can see that there is a maximum here. That is the highest point that our value reaches, but we don't necessarily have a relative minimum, because even within the domain we can see that this is kind of continues and goes on. But we can see that we do have a local relative maximum or a local maximum, and it's going to be located at the point 2, 4. So going back to the minimum, this is going to be none. And again, it's none because this is kind of going on forever. And as we look at the open interval, it'll increase infinitely. And so we will never actually get to a minimum there. All right, let's take a look at the next example. So we want to graph the function f of x cubed minus 6x squared plus 9x plus 1 in specifically this graphing window. So we're limiting it to -5, 5 and -5, 5 on the y and the x. So we want to state the intervals in which the function is increasing. So we want to be able to identify increasing. We want to be able to identify decreasing. And we want to say any relative maximums or minimums or local min and maxes. So I have the function already graphed here on Desmos, but we want to make sure that we're paying attention to the interval which they asked. So there's a couple different ways here. You can actually go to here to graph settings, and you can actually change the axes here. So we want to make sure that we go ahead and change this to -5 to 5. So we're looking at the exact same window that they had kind of mentioned in that problem. So we're going to be looking at -5. And then we're going to change this over to 5, looking here at -5, and again to the y for 5. And then we can kind of close out of here, and we can see that this is where we want to be looking at. And so I'm actually going to, because I don't think it's recording everything. There. So we want to be able to be in that window, right, from -5 to 5. We want to be able to see all of the different extremas, so the minimums and the maximums. So we can tell that it's increasing from -5 to 0, right? So from in that interval from -infinity to it's going to increase to right around here, which that looks like it might be 1. Now we go from 1, we start decreasing down to 3. So we're x equals 3, and then we start increasing again from 3 on to infinity. Our minimum here, we're going to have a local minimum right here at this point right here, which looks like it's at when x equals 3 comma 1. And then we have a local maximum at this point right here. We're looking at when x equals 1 and we have y equals 5. Okay, so those are all the values that we wanted to kind of mention. So let's kind of write all of that down. So we are going to be increasing in the interval. There we go. We're going to be increasing in the interval from negative infinity. I believe it was to 1. We'll check that right now. And then union. So let's go ahead and check that right now. So negative infinity all the way to 1. And then we are increasing again from 3 to positive infinity. We are decreasing then from the interval from 1 to 3. We saw that we have a local minimum at, I believe it was 3 comma 5. And we have a local, oops, my local minimum was at 3 comma 5. And then my minimum was at, I think I got these backwards. Hold on, let's just double check these. So my local maximum is at 1 comma 5. My local minimum is at 3 comma 1. So I was getting those ones confused. Let's come back over here. So local minimum, local max. So local minimum was at 3 comma 1. My local max was at 1 comma 5. And that's what we wanted to do for that problem. Just identify based off of the graph. Okay, and that ends this section. Let me know if you have any questions.